So in this video, we'll talk about integrated integration. So what is this? This is a process of repeatedly integrating, repeatedly integrating the results of previous integrations. All right. So, for example, if I integrate from C to D, the integral from h1 of y to h2 of y of f of x y dx with respect to y. All right. So how do we solve iterated integrals? Okay. We evaluate from the inside out. So we work from the inside. So we evaluate from the inside and we'll work our way to the outside. So we'll do this inside part first. And then once we get that, then we'll integrate with respect to y on the outside here. Okay, so the x is what I integrate with respect to first. I integrate with respect to x first. Okay, so x varies from curve to curve. What do I mean by that? The first curve is x equals h1 of y to x equals h2 of y, right here, right? And then once I get done integrating there, I then integrate with respect to y from C to D. So y varies from constant to constant. So from y equal, if I integrate with respect to y, I have y equals C up to y equal D. Okay? So the inside integral produces a function in terms of y, since my limits of integration are h of y and h of y, yeah, h1 of y, h2 of y. The outside integral, when you integrate that, it produces a function with respect to y. Okay? So, if I do it the other way, all right, so that had a dx and then a dy. Now I'm going to switch these roles around. And I'm going to integrate the integral from a to b. And then the integral, iterated integral, from g1 of x to g2 of x, f xy dy dx. So now I've switched it around. Okay. So how do I do this iterated integral? I start from the inside and work my way out. So if I work on the inside, what do I integrate first? I integrate this inside piece first. Okay. So in a picture, what am I going from? My y values are spanning between g1 of x and g2 of x. Okay. So in a picture, what does that look like? My x values, I have my y values. All right. So this would be y equals g2 of x. And then this one would be y equals g1 of x. So the y value between those two, that's all the y values between those two there. And then what am I doing? I'm integrating with respect to x between a and b. So my x values are stuck between a and b. So whenever I integrate the inside piece here, I'm integrating from curve to curve, and then I'm integrating from point to point. Okay? So curve to curve, and then point to point. And point is a constant. Okay, so if this represents x equal a, and that represents x equal b, then you look up here, this is actually the region R, is the area between those two curves, G1 and G2, and restricted from x equal a to x equal b. All right, so we are adding. When I do integration, we are adding up the heights of the function. What am I adding up? I'm adding up this function, which that is just some function in terms of z. That's my height, how far I am off the xy plane. So we are adding up the heights of f of xy over what region? Over the region R bounded by g1 of x less than or equal to y less than or equal to g2 of x, and a less than or equal to x less than or equal to b. All right? So let's just think about it. Think about it for a second. What's going on here? Okay? The integral from a to b of g2 of x minus g1 of x dx. Remember when we, some of y'all remember when we did this in Cal 2, okay? When we had two functions and we were subtracting, what did we think about it as? We thought about it as top function minus bottom function. Yeah? Okay? And so when we did this, it would produce a region that looks kind of like that. Right? So let's go back a step here, and I'm going to integrate g1 of x to g2 of x of 1 dy. Okay? So what is the integral of 1 with respect to y? The integral of 1 with respect to y is y to the 1. And I plug in from g1 to g2. And so this produces f of b minus f of a, which is g2 of x minus g1 of x. Okay? Now, what do you notice? This is the same as this. So I can plug this in for that right there. And what's that going to get me? That's going to get me the integral a to b, the integral g1 to g2 of 1 dy dx. Okay, you'll see how this is the same thing. Yeah, I'm plugging it in here. Okay, and this is equal to integral a to b g1 of x, or g2 of x rather, minus g1 of x dx, which we just talked about that being that region right there. Right? Now, what is this saying to do? How do we read this? So I'm integrating, I'm adding up heights of 1. Okay, so my function f of xy is equal to 1. So this has a height of 1. So I'm adding up heights of 1. Right? On what region? On the region where y is bounded between g1 and g2. So y is stuck between g1 and g2. And x, oh, that's hard color to see. X is stuck between a and b. So that's that same picture we just drew up there. Okay, that region is this region right here. Okay? And I just showed you that that is equal to this thing right here. Okay? So the area R, you think of this area, all right, in a three-dimensional picture here. If this was volume, the height of 1 would, well, when you multiply by 1, okay, that doesn't change anything. So that area and that volume, okay, would be that same number there. All right? 1 unit thick. So here's a idea. 1 is a constant that we are adding up. So we give all the area in this region, this yellow region, a weight of 1, and everything else that's not in that region, a weight of 0. Okay? So here's the theorem for you. 13(1,1), area of a region. Area of a region. A is equal to the integral from a to b, g1 of x to g2 of x, of 1. We integrate 1 over this region to find the area. Okay? So what does that look like? In this scenario, we have x equal a to x equal b, g1, g2. So the region, the area here, to get this area, is that iterated integral right there. All right? Now, if a equals the integral from c to d, integral h1 of y to h2 of y of 1 dx dy. Okay, so we change the order now. All right, so now that the order has changed, what does this tell me? It tells me integrating with respect to x from here to here. So x is stuck between h1 of y and h2 of y. Okay, and the y is between c and d. All right, what does this picture look like? So this is the scenario where now x is a function of y. And so that means, so this is h1 of y, so x equals h1 of y. And then this is x equals h2 of y. And then the constant y equals c to y equals d here. And so my area here, what I'm finding is this region. Okay? So I don't know if you remember when we were in Calc 2, but we would say, you know, this top one here would be x easy because we have these constants. We go from curve to curve, point to point. The point to point would be in terms of x, so that's x easy. And then here we would say that this is y easy because it took one integral to calculate that area of that 2D region. Okay? All right, so let's do an example here. So we're going to do an example. We're going to find the area A of the triangle with vertices 1, 1, 3, 1, and 5, 5. Okay? So first thing I need to do is I need to draw a picture. All right, so I'm going to find the area of the region. So from 1, 1 to 3, 1, and then 5, 5. So 1, 1, 3, 1, 5, 5. All right, so whenever I draw or whenever I look at this, if I was going to do dx slices like in Cal 1, it looks like this thing would turn into two different tops. So we have one here, and we'd have to have a new integral here because the bottom is not the same for those two. All right, the tops are the same for both of them, but the bottom are different. So we'd have to have two separate integrals. So it doesn't look x easy. What about y easy? Does it look y easy? Is the left always the left and the right always the right? If I draw this dy, everywhere I go through here, the left is always the left side, the right is always the right side. So that definitely looks to be y easy. Okay, and if you need a refresher on the y easy topic, go to my Cal 2 lessons or the videos on YouTube and go look up the y easy integration. Okay? So what does y easy look like? Y easy is this scenario here. Okay. And so we are going to integrate with respect to x and then with respect to y. That's y easy. All right. So I integrate x between or from curve to curve. And then I integrate y from point to point. Okay? So x, the x value, all right? What is it between? All right? So when I look at this, I have an equation here and I have an equation here. All right? So I need to figure out what those two things are because x is varying between those two things. All right? So this one, 1 to 5 5, that one's actually not too bad. To make a line, I need a slope and a point, don't I? So the slope from 1 to 5 5, that's 5 minus 1 over 5 minus 1, which is equal to 1. And then 1 is the point. So y minus 1 equals 1 times x minus 1. So this gets me y equals x for that line there. Okay. Now, for this yellow line over here, my slope, a little bit more complicated. It's not that bad though. y2 minus y1 over x2 minus x1. So that's 4 over 2. So my slope is 2. So I have a point y minus 1 equals 2 times x minus 3. If I do that math out, y equals 2x minus 5 is the equation for that line right there. Okay? So x it spans, the x value spans between two curves. So two curves where h is a function of y here and h is a function of y here. Now, right now, I have y as a function of x, but that one's pretty easy to flip around. All I do is I just flip it around and I'm done. So this is y, okay? But I can't just write 2x minus 5 over here. That doesn't make any sense because that's not a function of y. So how do I rewrite this to be a function of y? Well, I take y equals 2x minus 5 and I solve, right? Remember, this is x equals something in terms of y. Okay, so I need to solve for x here. So how do I do that? How am I going to fix this? I'm going to add 5. So I get y plus 5 equals 2x. I'm going to divide by 2. And so I get x equals y plus 5 over 2. Okay? So my x value runs from this side here, y equal x, which is x equal to y, and then y equal 2x minus 5, which becomes x equals y plus 5 over 2, right there. All right? And then the y value runs from what to what? It runs from point to point. So the lowest y value the lowest y value goes from what? It goes from 1 up to the highest y value, 5. So I run from 1, y equal 1, to y equal 5. And that's going to cover the whole span of that triangle. So the y value goes from point to point, 1 to 5. Okay? The hardest part of this problem is figuring out the region. All right? And when you figure out the region, you're trying to figure out that R region here. Okay? All you're doing is trying to figure out, how can I describe this triangle area R in terms of curve to curve and point to point? And since this was y easy, okay, then it makes sense to do with respect to x first, right? Curve to curve with respect to x, and then point to point with respect to y, because it's y easy. You only want to have to describe it with one region. All right, one iterated integral. All right, so now that we have the setup, let's do it. So what's the formula say? It says I integrate the function 1 from curve to curve and then point to point, dx dy. So this is equal to the integral, iterated integral from curve to curve, so from y to y plus 5 over 2 dx, and then remember, integrating this, and it's x spans from those values right there, okay? And then the second part, I'm integrating with respect to y, okay? So integrate with respect to y from point to point, so from 1 to 5, right there. So integrated integral, I work from the inside out. Integral of 1 with respect to x is x from y to y plus 5 over 2. And whenever I do f of b minus f of a, I get y plus 5 over 2 minus y dy. All right. And then what would I do? I would integrate the pieces, all right? So you could write this as y over 2 plus 5 over 2 minus y. All right, this actually could simplify. I could combine half a y with a full negative y to get integral 1 to 5 of 5 over 2 minus y over 2 dy. Integral is 5 over 2y minus y squared over 4 from 1 to 5. If I plug in 5, I get 25 over 2 minus 25 over 4 minus, plug a 1 in, I get 5 over 2 minus 1 over 4. Oh gosh. All right, do the math there. Should get 4. Okay? Should get 4. All right. How do I know it's 4? Because a triangle's area, right? How the base here is 2. So what is it? Base times height divided by 2, right? Area. So the base is 2. The height is 1, 2, 3, 4 divided by 2. That should get you 4. Okay? That's what it should be. All right, now look. We can do this same problem, and we can do it in the x direction, because we just did it in the y direction, dx dy. But what if we did dy dx? I would actually have two integrals. All right, so I'm going to show you what would happen if we did this the other way. I think it will be good for us to do it this way to give us a little bit of practice, all right, on how to set this up. Okay, so if I did, x easy, all right, what does that mean? That's the integral, double integral over the region R of 1. And then it's dy dx. So all the same stuff applies here. All right, we got our equations. We calculated all that junk. All right, so I don't need to write all that again. Okay, so I have my two equations. This is for that line, and then this is for this line. Okay, so this says to figure out y from curve to curve. So this is y equals something in terms of x, and this is curve to curve. And then integrate on the outside, x from point to point. All right? So this is actually going to have to be split up into 2. Okay? So the y value, y is stuck between curve and curve. So the top, the biggest the y value ever gets is what? The biggest the y value ever gets is y equal to x. Okay? So something in terms of x, that's x. What is the smallest the y value ever gets? The smallest the y value ever gets is 1. Okay? So this is the function y equals 1. It's always 1. This horizontal line is a constant function here. So y is stuck between those two values. Now, the x, okay, what is the x stuck between? The smallest the x value can be, smallest the x value can be is 1, and the biggest the x value can be for this first part is 3. So x is stuck from point 1 to point 3. So from point to point, 1 to 3. All right? So what does that look like? To get the area of this region, I do the integral from 1 to 3, and then from 1 to x of 1, and then I integrate from 1 to x the y value, and then I integrate, I add up all the x's between 1 and 3 right there. Okay? So that's the first part. All right? So if I did this, what would that be? The integral of 1 with respect to y is y. So from 1 to x. Okay, so this becomes integral 1 to 3 of x minus 1 dx. So that's x squared over 2 minus x from 1 to 3. All right, which is equal to, was that equal to 2? All right, be 9 over 2 minus 3 minus 1 over 2 minus 1. And then f of b minus f of a. We should get 2. All right. Let's do it for the second part of the triangle. So up here, okay. So if I'm going to do this, I need to figure out what does, so y equals x here. Now here, y equals your 2x minus 5. So the y value ranges between x and 2x minus 5. Okay? And then the x value spans between 3 and 5. So I'm going to have to integrate. To get this region's area, I integrate from 3 to 5, from x to 2x minus 5 of 1 dy dx. Okay? And if I do all that math, integrate with respect to y, I get y from x to 2x minus 5, which is equal to the integral 3 to 5, 2x minus 5. Sorry. Excuse me. Minus x dx. All right. You can clean that up a little. 3 to 5 of x minus 5. Integrate with respect to x, that's x squared over 2 minus 5x from 3 to 5, which if you do that math, you'll get 2 as well. And 2 plus 2 gets you 4, which is the answer that you wanted above. How about that? All right. So you can do it either way, but you clearly see that I think that this way is actually harder because you end up with you have to calculate 2 iterated integrals to get that area, just like when you were in Cal 2, if you did x easy versus y easy, you ended up maybe causing yourself to do twice the work. You could have done it in half the time if you chose the correct method. In this case, y easy gets the whole thing with one iterated integral.